Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn how sound builds up and decays in enclosures like rooms.
So let's get started. We know intuitively that the sound fields in rooms or enclosures are fundamentally different than the sounds that we hear outside in the free field. And this is because if we are in a room with a sound source, what we hear is not just governed by direct sound, but is also governed by reverberant sound, because the direct and reverberant sound fields add up at our ears. And these reverberations may be affected by acoustic treatments in the room, furniture, open doors. So if we want to answer the question, what is the sound pressure level in this room, we need to learn how sound builds up in space. The sound field that we encounter in an enclosed room is called a diffuse field. The diffuse field means that for any given sound element in the room, the likelihood of energy flow away from that sound element is equal for any direction. So sound is just as likely to flow up as it is left, right, and so on. In order to model how this diffuse field builds up, we consider a conservation of energy equation, where a sound source with acoustic power, capital Pi, is placed in a room. The total rate of change of energy flow into the room is governed by this conservation of energy equation. It reads V, which is the volume of the room, of course, units in meter cubed, multiplied by the rate of change of the average acoustic energy density, capital E, T, average acoustic energy density, the units here are joules per meter cubed, plus an absorption term, which is capital A, room absorption, having units meter squared. We'll introduce this variable in greater detail soon, multiplied by C, the sound speed, divided by 4, multiplied by the average acoustic energy density once again, is equal to the sound power. So the time rate of change of energy flow into the room is equal to the sound power input minus that part absorbed by the room. Now we've moved this absorbed part to the left-hand side of the equation so that we group together our variables E. We see that this is a first-order ordinary differential equation, which we could solve, for instance, by using a Laplace transform. And when we do so, we find that the average acoustic energy density E as a function of T is equal to 4 times capital Pi, that sound power source, divided by AC, the room absorption, multiplied by the phase speed, multiplied by 1 minus E to the power minus T divided by tau E. Let's look more into this solution. The time constant that we found, tau E, is equal to 4 times the volume divided by AC. If we plot out our average acoustic energy density in a normalized time axis, we see that after around 5 or 6 of these room time constants, we arrive at the steady state acoustic energy density. So our steady state level is shown here, since our y-axis is normalized with respect to the steady state. We see that the room absorption A shows up in our steady state value. It's the quantity of the sound energy absorbed by the room. Now, if we think that the room is perfectly rigid, this is a case where the room absorption goes to 0. And that would mean that our steady state acoustic energy density goes to an infinite value. Now, of course, this is not intuitive. If a sound source is placed in a room, the volume doesn't infinitely increase. And that's because we have neglected the small but meaningful intrinsic dampening of the air in this approximation. So this signifies the sound that builds up when a source is placed in the room. Intuitively, we know if that source is turned off, sound will also decay. So after the sound source is turned off, the same first-order build-up is observed in a first-order decay. The solution for that sound decay is shown here. The average acoustic energy density is equal to the original acoustic energy E naught, which could have been the steady state value, multiplied by the exponential e to the minus t divided by tau e. Now, if we consider this as an exponential decay, on a logarithmic scale, this sound decay is linear, and we could plot that out in decibels, where we have 10 log 10 of the quantity E divided by this steady state value, 4 times pi divided by AC. Let's focus in on this logarithmic sound decay. We define something called the reverberation time, and it's how we quantify 60 decibels of this sound decay from steady-state diffuse field sound pressure level. This reverberation time is equal to 0.161 times the room volume divided by the room absorption A. This assumes the room is filled with air, which is very likely given the practical use of this reverberation time. Now, the way in which we would determine this is from measurements. It's determined also on an octave band basis, since the reverberation time T60 for the octave band of 125 Hz might be different than the reverberation time T60 for 4 kHz, for instance. So let's consider an example. To measure the reverberation time, it's best to be done in a highly reverberant room. Very often, these things are mounted on the ceilings called diffusers that help to create a very equal sound space where the sound energy is equally distributed in the room. Either someone claps in the room or another impulsive sound is released so that we can hear the decay of sound in the room. Now that's a long reverberation time, but we want to process this using a short time Fourier transform. And when we do so, we see that the sound pressure level peaks very quickly with the spike of the clap and then decays. And we see that when we plot this out in time in a linear axis and sound pressure level, we see a mostly linear decay. And we could approximate a line from this decay. If we did this for higher frequencies, what we see is that this slope is a little bit steeper, whereas for lower frequencies, the slope is slightly more shallow. So the reverberation times for lower frequencies tend to be greater. We especially see this at 250 Hz. And the slope for 4 kHz is much more steep. And now that we've got our data, we can approximate T60 for each of the octave bands by creating a linear approximation of this slope. The time required for this slope to reach a 60 decibel drop is the T60. Now, our data might not show a 60 decibel drop. Take, for instance, 4 kilohertz. We don't have a 60 decibel change from 70 dB to the sound floor of 20 dB. In other words, this microphone does not appear to register any sounds quieter than about 20 decibels. And in this case, we approximate the slope only over the approximately linear portion of the curve, extend this out by extrapolation to 60 decibels, and determine the time required for that slope to pass through 60 dB. Now that we know all about reverberation times, what does this mean when it comes to reverberation times for practical rooms? There are many recommendations for how to optimize T60s for distinct room uses. Ordinarily, the need for speech intelligibility and sound discrimination, for instance in music, are central aspects to optimize reverberation times. Take, for instance, this list of recommendations that's shown on the right. For reverberation times that are less than about 0.4 seconds, we consider this to be acoustically dead. The room feels more anechoic, without echo, than it does to have moderate reverberation. For environments where we need to hear speech clearly, very often the reverberation times will be between about 0.4 seconds and 1 second. Whereas in environments where we might have speech and music, like in theaters, restaurants, and offices, the reverberation times are often a little bit higher, from about 0.8 seconds to about 1.2 or maybe 1.4 seconds. And when we're in environments where we're specifically listening to music and performances, often the reverberation times will be greater than 1.4 seconds. And especially so for classic worship music in churches, where choirs and organs are heard. In those cases, the reverberation times might even approach 3 seconds. There are also correlations in this table to the volume of the room involved. So for instance, a classroom is small, whereas an office space might be larger, but in both environments we want to hear speech. What we see though is that as the volume of the space increases, we might still permit greater reverberation times, even if we're still interested in the same function, and that is speech. So let's summarize what we've learned. We've learned that sound builds up and decay in enclosed rooms as a first-order process. On a logarithmic scale, this sound decay is linear, suggesting a linear dB or decibel per time slope. And we quantify this by the reverberation time, T60. It's a measure of the sound decay in dB for each octave band. Nominal reverb times are cited for many different spaces depending on the use of the room, and T60 can be estimated given knowledge of the room absorption.
That's it for this video. We've learned that when sound sources in rooms are turned off, the sound levels decay with time. In the next video, we'll learn about room absorption, which helps to explain this sound level decay.